All right, welcome to another exciting episode of AP Chemistry here at Spain Park. Today is Friday, November the 14th, and what are they supposed to do?
Hit that like and smash that subscribe button and ring that bell.
There you go. Okay, we're striving for 250 on the subscribe. Okay, let's go. All right, so when we're drawing a Lewis dot structure, what's the first step?
Add the electron.
Count the valence electrons, y'all. You cannot do these without doing that. So we have 6 and then 6, and so 18, so you end up having 24 electrons. Then what?
Then
What's the? How do you know what the central atom's going to be?
Furthest left.
Furthest left, but also just the one you have the least of. Okay? So in case sulfur, and then we're just going to build around it with single bonds. Always build with single bonds. And each line represents how many electrons?
2.
2. Now, listen. A lot of people are just jumping in saying stuff, but if there's ever something you don't understand, ask the question, okay? Don't let the aggressive people overshadow you if there's still something that you don't understand, okay? So make sure to ask the questions on this.
Is it, so you're looking for us to put the amount of electrons we get, right?
Well, I don't care if you write it down.
Okay.
You just have to do it.
Okay.
I'm looking at this, okay? But if you don't do that, you're not going to get this right. I don't say, not if you don't write it down, if you don't count, okay? So if you just keep in your head that it's got to be 24, I don't care if you write it down or not. And AP doesn't care if you write it down or not. They just want you to draw the Lewis dot structure. Okay? So it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24.
Ooh.
Okay? So that's all of my electrons. But what's the problem?
You're missing
Sulfur.
Sulfur. So when the central atom does not have enough, what do?
double bonds.
Form a double bond. Steal from the rich. And the rich, in this case, all of these are equally rich. Okay? So we're just going to go here. I could have picked either one. So let's go. Get your notes out, because I'm going to kind of teach something right here. Okay?
I don't have it.
For some reason I feel like you might be communicating. There's this thing called resonance. Well, let me back up. There are 2 ways. Okay, so when we're in covalent bonding, page 2 of covalent bonding. Okay, page 2. Now, so the first page is ionic and metallic, and then you go to covalent. And on page 2 of covalent, it talks at the top about sigma and pi bonds.
Whoa, that is not easy.
Is it not?
Nope.
It's gotta be.
Sigma and pi.
The very top.
Hybridization. The 4th page.
Fourth page of notes, but the second page of covalent, right? Yeah. When orbitals bond covalently, when they share, okay, there's 2 ways in which the orbitals can overlap, okay? And the first way, 2 ways orbitals overlap. And again, this is in your notes. The first is called a sigma bond. And that's going to be, Steve, a sigma bond. Any and all type of orbitals can form a sigma bond. So if I take an s orbital, okay, you guys did check in, okay.
We're late.
Yeah. Oversleeping at 11 o'clock class. School is too easy these days. Okay? In a sigma bond, if I take an s orbital, I overlap it with another s orbital. Here's the overlap of the electrons. It lies on a line drawn between the 2 nuclei. Okay? Now, The actual bond, what makes it a covalent bond, what holds them together, is the electron from this atom is drawn to the nucleus here. The electron from this atom is drawn to that nucleus. So this pair of electrons in between is being equally pulled this way and that way. That's a sigma bond. It's the first bond between any two atoms is always a sigma type bond. It's the strongest, the greatest degree of overlap. So if it's a single bond, it is a sigma bond. Okay? An s orbital, jeez, that messed me up. An s orbital and a p orbital can form a sigma bond. Here's the overlap, and the overlap lies on a line drawn between the two nuclei. The electrons are here. This is where the greatest electron density is going to be. It's going to be between the two nuclei right there. It's a sigma type bond. Any and all type of orbitals can form a sigma bond. S with S with P, two p orbitals, D's, and what we're going to learn about these hybrid orbitals can form sigma bonds. The first bond is always a sigma type bond. Okay? But the second bond is a pi bond. And only p orbitals can form pi bonds.
P for pi, if I get it.
Okay? Only p orbitals can form pi bonds. And it's going to be a side-to-side overlap of p orbitals, where it's here and here. Here's the two nuclei. The overlap does not lie on a line between the two nuclei. It's a much weaker bond, much less overlap. But the second bond of a double bond and the second and third bonds of a triple bond are always pi bonds.
Wait, can you say that again?
The second bond of a double bond and the second and third bonds of a triple bond are always pi bonds. Okay? So, multiple bonds are always going to be pi bonds. Single bonds are always going to be sigma type bonds. Now, this is going to be real easy as far as to count. I'm going to come back to this here. But if I draw some kind of crazy compound,
A lot of C's.
notice that carbon can always form 4 bonds. It can form 4 single bonds. It can form a double and 2 singles. It can form a triple and a single. Carbon can always form 4 bonds. It's got 4 valence electrons, so it's going to form 4 bonds. Okay? So if I'm looking at this, if it's a single bond, I know it's going to be a sigma bond. So sigma, 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 sigma. Double bond, though, the first bond is a sigma bond. The second one is a pi.
No matter which.
Doesn't matter which one. Okay, when we start doing this hybridization today, then we'll see that come into more play. Single, sigma, sigma, triple bond, sigma, but the next 2,
Pi.
pi, pi. Sigma, 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 sigma. First bond, I know that you guys have made something stupid out of sigma, but I'm going to say it 1,000 times today, so we're just going to have to get used to it. Okay? So we can just count sigma and pi bonds, and the key is to know that only p orbitals can form pi bonds. Any and all type of orbitals can form sigma bonds. Only p orbitals can form pi bonds. That's going to be important. Now, all right. We're going to hold that thought. I'm going to come back to this. I really thought I could go into this right now, but I was going to explain the concept of resonance, which we talked about, but I think I'm going to do hybridization first, and then I'm going to come back and do resonance. Okay? But we're going to keep tabs of this sigma, sigma, pi, pi, all that stuff. Okay? thought I had a good idea, and then I changed my mind and said it wasn't that good of an idea. All right, so let's go back and let's finish looking at these Lewis dot structures. You all feel pretty confident in them. You guys both have the worksheet completely done? Okay. So we have here, we have the double bond. And it looks like that. Now again, it doesn't matter which oxygen you have the double bond on, and that's what I was kind of trying to go to, but I'm going to come back to that hopefully at the end of the class today. Okay? So HNO2, what do you remember here? So first off, we count electrons. How many electrons do we have? 1 plus 5 plus 6 times 2 is 12. So 1, 5, and 12 makes 18, right? So 18 electrons. So what's my central atom going to be? Nitrogen. Okay, remember it's never hydrogen. Hydrogen's too small, even though there's only one of each one. Hydrogen is never the central atom. So it's going to be nitrogen. And oxygen, oxygen, doesn't matter where you put them. You can put them, 90 degrees. You can put them up and down. Doesn't matter where you put them. But what about the hydrogen? Always goes with the oxygen. So it doesn't matter which one. I'm just going to put it over here. You can put on either one. Okay? So now I have 18, 2, 4, 6. Hydrogen only needs 2, so we don't put any lone pair. Hydrogen's never going to have a lone pair. Okay? 2, 4, 6, 8. Everything's trying to get 8 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So what do we need to do? Okay, so with which one? Well, how do you know that?
Because the other one is hydrogen.
Okay, the other one's full. The other one's already got it's got its 2 bonds. Oxygen is going to want to form 2 bonds, but sometimes there's one. I'll show you carbon monoxide. You can form 3, but we're going to steal from the richer. This says 2 lone pair. This says 3 lone pair. So we're going to steal from the one that has more lone pair. So we're going to steal from this one and make the double bond. Okay, steal from the richer. SiO2, got 4 and 12, so now I have 16 electrons. Si, oxygen, oxygen, okay? So 2, 4, 6, 8, 10, 12, 14, 16. Uh-oh. So now I need, silicon needs 2 more pair. So I'm going to steal, but you don't need to steal both from the same one. Steal here and here. Okay? You probably want to form 2 doubles before you form a triple. If you can. Okay? I3 minus. What does the minus mean? So 7 times 3 is 21, plus 1 is 22 electrons. It's pretty obviously iodine is going to be the central atom. Okay? It's only one way. I mean, even if you did it in an angle, it's going to be fine. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But now I have the opposite. Now I have too many electrons. So where do the extra 2 go? Always on the central atom. Extra electrons always go, always in pairs. You're not going to put like 1 and 1. Don't put them, and don't do that. Because then it's confusing thinking, is that part of the single bond? Or is that, a lone pair? So don't put them right there. Okay, what I do is just when I'm doing this, is I just go ahead and just kind of just do that. Then I'm just going to have the 2 pair down here. Okay? Now, since it's an ion, what else? Brackets
Minus sign.
with the minus sign. Okay, this is a question. Highly missed question. Global point total out of 1 point. The average grade globally was 0.1 out of 1. Okay? So only 1 out of 10 at the most got this right. if I3 minus is dissolved in water, what is the name of the attractive force between the I3 minus and the water?
Ion-induced dipole.
Say what? I heard, what did you say?
Ion-induced dipole.
No?
Ion dipole.
Okay? Why would you say induced dipole? Which one's the induced? Okay? What did you say over here? Ion dipole. Water's the dipole. This is an ion. Almost everybody was saying dipole, dipole. Is this a dipole?
No.
No, it's a monopole. It's only negative.
Monopole.
It's not a dipole. Polar molecules, positive and negative, are dipoles, two poles. This is just negative.
Wait, what is ion-induced dipole again?
And any ion
Yeah.
attracted to water.
No, I said, what is ion-induced dipole?
Oh, that would be if you try to put it in a nonpolar. It wouldn't be soluble at all. That's going to be super weak. Okay? That's one of the things. We went over the whole test from last year, and I was actually going through everybody's answer books from last year and looking at the responses, and
Mr. Alpha's crashing out on some of
I was. Seriously, I mean, how many times have I made you talked about knowing your intermolecular forces and all that? Ion dipole. Okay, so I'm going to start going super fast now, okay? And I'm just going to highlight some. This is, right when I say that, I see this one. I don't know, have y'all ever heard of a CFC in terms of environmental issues? CFCs being bad for the environment? A CFC is a chlorofluorocarbon, a carbon compound that's got both chlorine and fluorine attached to it. They're used a lot in refrigerants, car air conditioners, your refrigerator at home, some air conditioning systems in your cars use chlorofluorocarbons, okay? And so they compress into a liquid, but then they're very volatile. They evaporate very quickly. When they evaporate, they get real cold and they make great refrigerants, okay? But it's a chlorofluorocarbon. So again, I'm gonna say count 4 plus then 28, so I have 32 electrons. Carbon, it doesn't matter where you put them. When we start looking at the shapes and everything of these, we can come back and kind of see. But this is a chlorofluorocarbon, so that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay? I'll come back and we'll talk about the shapes after we draw all these. NF3 is just going to look like this once you count it and do it. Okay, make sure you have it like that. BRF3, that is going to be 7, and then another 7 times 3 is 21, so you have 28 electrons on BRF3. BR, F, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Where do the extra electrons go? Central atom. So again, rather than redoing it, I just do that. Okay, but it's always, you always have to have pairs. Never have single electrons. Unless there's an odd number. If there happens to be an odd number, then you'll have one unpaired electron. It's going to be called a free radical. It's highly reactive, but you just put it like a lone pair. You just put one. All right, before I erase all these then, what's my AX formula on this? What would the AX formula be? AX3, so what's the shape going to be? Trigonal planar. Trigonal planar. What does planar mean?
Flat.
Flat. It's a flat triangle, and we'll build some of these here in a second. Now, here you have 2 lone pairs, so you got to say the shape around each lone pair. You don't have an overall shape of the molecule. You have the shape around each central atom. So around this one, it's going to be A, X2, E. Just not E2, just E. E is pair. How many pair of electrons, not how many lone pair. So it's AX2, E. Now, just so you know, that is not an answer to anything. That is never an answer to anything. That's our clue to get to the answer. AX2E is always going to be what shape? Bent. That's your answer. Now I look at here, this one is AX2E2, but it too is bent. What's the difference between the two bends?
The degrees.
The bond angle. Okay? This one starts at 120. This one starts at 109.5 and goes down from there. This one's going to be what? AX2. And again, the lone pair, this is super important too. Lone pair are only on the central atom. When you're counting your E, don't worry about me. When you're counting your E, lone pair is only on the central atom. You don't count them on all the peripheral ones. Just how many lone pair on the central atom for your formula. AX2E is the number of lone pair on that central atom. Yes, ma'am?
Is there a way they could have like the N and the O, could it be like two different ones?
Yeah.
And then you have to state both of them, or
Yeah.
only the one on the nitrogen?
No, you state both of them. So you don't have an overall molecular shape, you just have the shape around each central atom. Okay? So this one though, it's AX2E, there's no lone pair on the central atom, so we know that that's linear. I3 minus, what's this one going to be? A, E, 1, 2, 3. Okay? AX2E3. Okay? So you're starting with 5, which is going to be trigonal bipyramidal. Okay? The 3 are going to come out the middle, so what's the shape of this one?
Linear.
It's linear. And I'll go over those a little bit more. This is AX4. It's tetrahedral. This is AX3E, which is trigonal pyramidal. And this one is AX3E2. Let me just go ahead and build some of these just so you can see what shapes they are. Yeah. Okay. Say that again, Cam. What you just told Adar. Don't trust what?
Don't base symmetry off of low stop structure.
That's exactly right. Because you're looking at something that's in 2 dimensions that's in really 3 dimensions. So even though it looks symmetrical, it's probably not going to be. Okay. So this is F. Go. Okay, look, in terms of shapes, now follow me. In terms of shapes, when you have 5 things that hate each other, 5 negatively charged things, they're going to arrange themselves in this shape, which is called trigonal bipyramidal. It's a triangular base, a pyramid on top and a pyramid on the bottom. Okay, so here's your triangular base with a pyramid going up and a pyramid going down. Trigonal bipyramidal. Now you have a 90-degree bond angles here, and you have 120-degree bond angles here. Because if an interior triangle, you know it's 360 all the way around, so it's 120, 120, and 120. Okay? Trigonal bipyramidal. Now, lone pair electrons occupy a greater space than bonding electrons. Lone pair electrons have extra electron-electron repulsions. This has a positive and a positive, help balancing out, help kind of stretching out the pair of electrons. But when it's a lone pair, now there's just nothing positive up here, so you get greater electron-electron repulsions in lone pair, so they take up a greater space. So when you have this, and it's got an option of having a lone pair come out of, this is called equatorial position, because like the equator, it's on the equatorial, versus axial, it's on a straight line like an axis, okay? Equatorial position, axial position. There's 120 degrees. There's much more room for the lone pair out of the 120 than there is out of the 90. It's going to be more crowded here than it is here. So the lone pair always comes out of the equatorial position. So if you have an AX4E, the shape is no shape. So they've made up shapes. They call it a distorted tetrahedron. It's four-sided, but it's all out of whack.
Seesaw.
But somebody said, hey, kind of looks like a seesaw. I see you, I saw you, I see you, I saw you, I see you, I saw you. A seesaw, okay? Or what I learned, a teeter-totter, okay? But seesaw is more fun to say, okay? So, but that's an official name. Seesaw is official name. That's easier to write than distorted tetrahedron. So the second lone pair is also then, if you have two lone pair, it too is going to come out of the 120 because there's more space for less electron-electron repulsions because they can spread out more. And so now I pity the fool that has this shape because it's T-shaped. Mr. T. I pity the fool. You guys don't even know who Mr. T is.
No, it's the Mohawk guy.
Yeah, Clubber Lang in the Rocky movies, but he was on the A-Team, if you ever saw the A-Team. Okay? T-shaped. So now we get to this one, which is AX2E3. So the third one comes out of the equatorial position. Now we're linear. Okay? So the lone pair are always going to come out of the one that gives you the greatest room, the least amount of electron-electron repulsions. Okay? So that's 5. If we go to 6, no, we don't go to 7. It's hot in here. These must be new. I think I bought a new set. We'll just go right here. 1, 2, 3, 4, 5, 6. Okay, so now we have AX6. This is going to be your sulfur hexafluoride. You're going to have sulfur with 6 fluorines around it. Each fluorine has its filled octet, no lone pair on the central atom. SF6. Okay? This shape, again, if I was there, they'd never ask me if the other one was trigonal bipyramidal. This would have been square bipyramidal. Instead, they call it octahedron, an 8-faced hedron. Octahedron. 4 faces on the top, 4 faces on the bottom. But notice it's 100% symmetrical, 90 degrees in every direction. Because it's 90 degrees in every direction, it does not matter where the lone pair comes out. So the first one, just pick one, anyone, it's a lone pair. So now we have square pyramidal. A square-based pyramid versus a trigonal pyramidal. A triangular-based pyramid. Okay? But now when we go to make the second one, the second lone pair, now again, lone pair occupy, they have greater electron-electron repulsions, so we're not going to want to make a lone pair out of one of these because the lone pair would be too close to each other, so the lone pair always comes off opposite, so that you minimize electron-electron repulsions. So now we have square planar. And usually you don't go much below AX4, E2. Square planar. Okay? All right. So those are the bigger shapes. When we go tetrahedron. Oh, geez, time flying when we're having fun. No. Oh. You've had 45 minutes. Oh, well, what? You had 90, you had 70 minutes free on Wednesday and Thursday?
No, no possibilities. I was watching. My bad.
Yeah. Two, three. I don't have another green one. Let me steal one. Okay, here we go. So when you have four, AX4, four things that hate each other get in the shape of a tetrahedron. Now we draw this. See, when you draw it, CH4, okay, this is what Cam was saying. You can't trust the symmetry based upon how you draw it. Because that looks flat, but it's not flat. It's three-dimensional. You're just kind of seeing it without any depth perception, where the one's on each side here and one out front, whatever. So if I change this and I put two hydrogens on here, I can draw it like this. Well, that looks very symmetrical now. But the reality is, like this, it's not symmetrical, because chlorine has a much greater attraction for electrons than hydrogen does. So the electrons are being pulled this way, the electrons are being pulled that way, and so there's nothing counterbalancing those. They're not opposite of one another, pulling equally and opposite like this drawing appears. So it's not symmetrical, even though it looks symmetrical there. So we're going to talk about how we know it's symmetrical probably on Monday. Okay? So, but that's the shape. So here's this. So, but if I take one lone pair, there's 100%, you know, here, 109.5 degrees every direction. So it doesn't matter where the lone pair comes. Take the lone pair. Now I have trigonal pyramidal, a triangular based pyramid. Okay? But the bond angle decreases just a little bit. Lone pair occupy a greater space than bonding pair. So it's going to like close the umbrella a little bit. There's going to be a little bit greater electron-electron repulsions. So these bond angles get a little bit smaller, about 2 to 3 degrees per lone pair. So now my bond angle started at 109.5, and now it's going to be a little bit less. For ammonia, it's 107.3. For other compounds, it's something less. It's different for every compound, but it's a little bit less than 109.5 because lone pair occupy a greater space. Now the second lone pair, doesn't matter where you take it from, this would be water, okay? Water is going to be like this. So now I have two lone pairs. So I started at 109.5, but now I have two lone pairs, each of which are repelling each other. So now my bond angle is down around 105. For water, it's 104.5. Okay? So 2 to 3 degrees per lone pair, bond angle decreases from what it would be if there were no lone pair. So this is a bond angle that's important to know, 109.5 degrees. Okay? I'm going to go here.
We're just playing with toys.
Do what?
So we're just playing with toys.
Yeah. Just trying to get all of my, I'm going to get them all built here. That's there. This can be here. And I need one more green one. Here. Okay? So these are just some of your shapes. I think trigonal planar is pretty easy to see. I don't need to build that one. Okay? All right. So we're all good here. Cl2O is just going to be oxygen, chlorine, chlorine. It's going to look like that. What's the shape going to be?
Bit.
Bent. AX2E2 bent.
It's like water.
Okay? Okay. Now, I need to throw out a couple of exceptions here. PCl5, it's just gonna look like this. Lone pair all the way around. What's my AX formula gonna be?
AX.
AX5, and so as a result, it's going to be
Trigonal
trigonal bipyramidal. That's going to be this right here. Okay, that's a very common. They use this compound all the time. SF4. SF4 is going to be 7 times 4 is 28 plus 6 is 34 electrons. So you're going to go 4 around it. 8 times 4 is 32. Where do the extra electrons go?
Central atom.
Put them anywhere, but in a pair, always in a pair, just anywhere. Now you can put it here, 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 here. Please don't put it on the actual axes, the X and the Y. Put them in the space in between. What's the shape gonna be?
Seesaw.
Distorted tetrahedron or seesaw.
Teeter totter.
Yes, ma'am.
Is it like incorrect if you draw like the bottom F like slightly angled so that you can fit the other 2 electrons there? Or does that-
Absolutely not. That's 100% fine. 100%. Again, it doesn't matter where you how you locate them. You just have 4 single bonds with a lone pair on the central atom. Now HCN. Okay, let's talk about this one. So we got 1 and 4 makes 5 plus 5. I got 10 electrons. Okay. Okay, Jonathan.
Bingo.
So we go carbon, nitrogen, hydrogen. And now how did I know carbon was my central atom? You got carbon and nitrogen. Fewest valence electrons, 4 versus 5. Okay, so 2, 4. Hydrogen doesn't ever need any more. 2, 4, 6, 8, 10.
We'll waste that little dot.
Yeah, I know. So what do we have to do?
Triple bond.
Triple bond. So we go here, and we go here. Okay? Now, it doesn't matter where the lone pair, typically I like to have the lone pair over there, but it doesn't matter where it is, because again, we're drawing in 2 dimensions. What's 3? Okay, we got a
Why did we triple bond it?
Okay? Carbon only has 4 electrons. It needs 4 more. So I got to share 2 pair to get the 4 more. And the only thing I can share with is the nitrogen, because hydrogen doesn't have any lone pair. Hydrogen can never form a double bond. Okay, you got to steal from your lone pair. You get your triple bond.
And we know to do that because you got to 10 before you even got
Yeah.
to carbon.
Exactly right. Okay? So what's the shape going to be? AX2 linear. Okay? SEBR3. So again, 21 plus 6 makes 27 minus 1, 28 electrons. So SE, BR, BR, BR. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Again, double bonds only occur when you don't have enough electrons for the central atom. Too many students try to do double bonds when you got more than enough. That just means you're going to have expanded octets. Only form double bonds when there's not enough electrons to satisfy the central atom. Okay? It's the only time you form a double bond. So what's my AX formula?
Is
3E2, so the shape is T-shaped. Okay? Now notice we have a noble gas. If I have a noble gas, first off, helium, neon, argon, no known compounds of any kind. But krypton, xenon, and usually they leave off radon because it's radioactive and it's got a very short half-life. Argon and krypton, krypton and xenon, under extreme conditions with the most reactive elements, they can make them bond with expanded octets. But it's going to have an expanded octet because they already have 8. So you know it's got to have more than 8. But you do everything exactly the same way. So it's going to be 8 plus 28, so you're going to get 36 electrons. So it's going to be krypton, fluorine, 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 to this, come on, Steve.
Stefan.
Okay, 8 times 4 is 32. So what do I have to do? Add two more lone pair. So I just always pick the spaces in between. But again, if you want to space them out, however you want to put them, you can do that. And then lastly, now this is an exception. Okay? You looked on ChatGPT on this one, is that what you said?
I said you gotta do the shape.
Oh, the shape AX4E2?
Square planar.
Square planar. Square planar. Okay? Does everybody know how to use, are you seeing on the form? Now, you don't have it pulled up. I have them run off for you over here, but, okay? BF3, okay, look, shine the light over here. Shine the camera. This little light. Here's an exception. You must know. If a group 13, specifically boron and aluminum are essential atom, they will have less than 8 electrons around them to make a stable compound. They're only going to need 6. It's an exception to the octet rule. So boron, aluminum, or gallium are the essential atom. You form stable compounds with only 6 around it. You do not have to form a double bond. Plus, remember, halogens don't form double bonds. So the fluorine in there is not going to be able to form a double bond, even though you probably have made one. Okay? Boron, aluminum, gallium, anything family 13 forms stable compounds with only 6 electrons around it.
Is that always?
Always. That isn't always. Now, they may form they could form a BF4 minus, where you put in an extra electron, so then the fourth F would fill in the extra spot, but you have to add another electron. But you're not going to form a double bond. So you're going to have you're going to have 24 electrons. So you're going to say boron, fluorine, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Typically, when you get to this spot, ooh, I got to form a double bond. When there's a group 13, you don't form the double bond. Plus, halogens don't form double bonds. They only form single bonds. But group 13, you're just going to keep it like this. So what's my AX formula?
AX3.
AX3. The shape's going to be trigonoplanar.
That's my nickel atlas, dog.
I said would, not will. Not allowed to bet. It's against the law.
Said I bet you a nickel.
How many would bet me a nickel? Not will. Okay? Are we feeling? Y'all, Lewis dot structures need to be simple. They need to be easy money. It needs to be low-lying fruit. We don't need to lose points drawing a Lewis dot structure. And we'll look at some of those practice ones
Monday.
later. Okay? But I want to get into all this hybridization stuff today.
Get money, yeah.
Okay?
So for the numbers, your team will be broken minus signs.
Oh, yeah. So, hey, so number 13, we're supposed to do this. Okay? Good call. Okay? Ions, you always put in bracket with the charge outside the bracket. All right, so that's the Lewis dot structures. That's the shape. But why do they have that shape? Okay? All right, hit pause on the camera.
Right back.
All right, so how do we get these shapes? Just when you thought it was safe to get back into the electron waters, we figured 1s2, 2s2, 2p6. We just took the test on it. Y'all did fairly well. And by the way, we had those 4 multiple choice questions there on the front page. If you noticed, if your grade, there was an 8-point curve on that test. Okay? 8 points. What?
It's because of the first
For
4.
those
Right?
4 questions.
Not because of those 4 that were on that first page. It wasn't the first 4, but it was.
Yeah, everyone
Like,
everyone listen.
It was actually.
Yeah, it was.
None that makes sense.
They were. There were a bunch. Yeah. So
I got 3
There's
of
some
4
real
wrong.
yeah, those were highly missed.
Utilize these as stories.
Those are very highly missed.
I got all.
You got all right?
I got all four wrong.
I got all four. Those are the only ones I missed. Wait, Dutch, what did you get?
Huh?
What did you get?
On the test?
Yeah.
90.
Like, with the 8 points?
Yeah.
Oh, shoot.
Alright, now this was before the last 8 people took it, so this number is even greater. Okay, so you can see on this one, 5, 10, 15, 20, 25 out of 38 missed this one. Okay, so explains the experimental phenomena of electron. What is diffraction?
Beats me.
Is what? That's the wave pattern of light, right?
I got that right.
Okay, diffraction is a wave pattern. Electrons give a diffraction pattern, okay, which explains the wave nature of matter is the fact that electrons give a diffraction pattern. And I wish we had time for me to show you the double slit experiment little video.
I think that's
States that electrons in the same order must have opposite spins. No.
I thought the rule.
No, opposite spins. It is not. Hund's rule says one goes into each before they begin pairing up.
That's the same thing.
It is not. Pauli exclusion principle says that only 2 electrons can go into any given orbital and they must have opposite spins. It's very much in the notes. Okay? Hey, why are you whining? You got 8 points. Even if you got it right, you got points for it. Okay? Pauli exclusion principle. Only 2 electrons in any orbital, and they must have opposite spins. Why do they occupy the 4s before the 3d?
That's probably
That is not Hund's. Hund's rule says you put 1 into each before they begin pairing up. It's the shielding. It's the fact that the 4s are less effectively shielded because they have the small but significant amount of time they get down closer to the nucleus. They're less effectively shielded than the 3D that stay out here and don't penetrate inside the core electrons. Gaseous, what does it mean to be paramagnetic?
It has one unpaired electron.
So on the 3rd energy level, okay, that's sulfur. If Hund's rule wasn't true and sulfur did that, would it be paramagnetic? No. But Hund's rule explains the fact that because if 1 goes into each, it causes sulfur to be paramagnetic because only 1 goes into each before they begin pairing up.
I think I put like Pauli exclusion principle somewhere.
Well, you obviously put wrong. Okay? Obviously,
What
a
is
bunch
that?
of people did.
What is the Pauli exclusion principle again?
Only 2 electrons in any orbital, and they must have opposite spins. What's Hund's? Heisenberg is that you can't know the exact position or the speed.
Bro, why couldn't that be a...
You can't know the position and the speed. That's why we have an orbital, not an orbit. Okay, that's why we have these things. That's why we have these shapes. The electron's just in the most probable place to find an electron. We don't know the exact path of the electron because Heisenberg says it's impossible to know both the energy and the position, the momentum, and the position at the same time. Okay? All right. Obviously, those were the most highly missed questions, which was the reason why you got that. Okay.
First page was
So hopefully you figured some of that out before you put answers onto your test corrections. It doesn't sound to me like you did. Okay? So maybe we won't get full points on the test corrections.
I got it right. Whoa.
Whoa! I mean, I gotta have my test corrections correct to have credit? Okay.
See, our teacher was curious.
All right. Now, why do molecules have the shapes that they have? Just when we thought it was safe to have the 1s2, 2s2, 2p6, when atoms bond and they come together, electron orbitals are all based upon the energy of the electron. Okay, first energy level, second energy level, 2p is a little bit higher energy than 2s. All their energies are all, their shapes of orbitals, everything about their electron configuration is based on their energy. Well, when atoms begin interacting with one another, their energies change. They start having more interactions with this electron cloud, with this nucleus. So electrons, we're going to kind of talk about two things at once. We're going to talk about hybridization and then the VSEPR, the valence shell electron pair repulsion theory, simultaneously, because they go hand in hand. The valence shell electron pair repulsion theory says that electron pairs repel themselves and they get the maximum distance apart. Okay? So it's kind of like there's a whole 2 or 3 pages of hybridization. Then there's another couple of pages of valence shell electron pair repulsion theory. I'm going to be talking about those simultaneously. Okay? They kind of go hand in hand. I just can't put them simultaneous in the notes. Okay? But it's all there. We're just going to talk about them at the same time. So, hybridization is a theory that's developed to explain how atoms bond, what happens. Basically, when atoms start interacting, the electrons are going to repel to get the maximum degree of, or minimize the electron-electron repulsions, maximum degree apart. How can they bond in such a way to where they can accommodate the other atoms and minimize the repulsions? The valence shell electron pairs are going to repel themselves and to get the maximum distance apart, form a shape where there's the least amount of electron-electron repulsions. And in order to do that, the orbitals change from atomic orbitals to molecular orbitals. They hybridize. So if I take a red rose and a white rose and I hybridize it, what color do I get?
Pink.
Pink. Okay? Or I get a red polka dot. Now if I get a red polka dot rose, is it a white rose with red polka dots? Or is it a red rose with white polka dots?
White rose.
If I say a red polka dotted rose,
It'd be white with red polka dots.
Nah.
A red polka dotted rose.
I think red
rose.
is white.
A red rose.
Yeah.
a red with white polka dots?
Yeah. Cause like a zebra's like black, but it's white. A zebra's white, but it's black.
But is it?
Is a zebra white with black stripes or is it black with white stripes?
Zebra's just definitely
Right.
Okay, anyway. The whole point is that the hybridized is kind of a mix of both. Okay? So when we hybridize orbitals, we're going to kind of, and orbital is the most probable place an electron can hang out. There's no walls, there's no barriers. So now all this means is the electrons are going to be hanging out in a different place, a different shape around the nucleus. So if I take an s orbital and hybridize it with a p orbital, I'm going to end up, my hybrid orbital is going to look like this. This is my s and a p. This is my hybrid. I get a fattened lobe, and it's got a little tiny little nub for the second lobe. Okay? Now, if I'm going to look at, and hybridization is only going to be with s and p orbitals. It used to be thought that the d's, but experimental evidence over the past 15 years or so have shown that d orbitals actually aren't involved in hybridization. We used to have hybridization with d's as well. Okay, so now, if we go through this, we're going to go through a 3 steps. So methane is CH4. And I don't know that, I really don't have enough room for this. But if I look at carbon, 1s, 2s, 2p, it's going to look like this. Okay, so if I was to draw the Lewis dot structure for it, I would have 2 electrons paired up here, and then 2 unpaired in the p's. That's my 2s and the 2p's. So if I really am going to make something with hydrogen, really I can just have a hydrogen come in here and a hydrogen come in here, and I would make CH2.
Mr. Hobbs.
Yeah.
Phone's a low battery.
Okay. But go ahead and pause it. CH2 doesn't exist.
I think they click.
Take your time.
Yeah.
Do what?
Is that-
You gotta get rid of the notification. It's covered by a little
Or
bar.
just take it out?
Oh, yeah, now you're just
No, I videoed.
No, he's doom scrolling chemistry.
In the normal atomic orbital state, CH2 is what we would think would form, but it doesn't. Okay? Experimental evidence says that it doesn't form. Are we not plugged in?
No, we're plugged in.
Okay. All right. So how can carbon form 4 bonds instead of just 2? Well, somehow we have to unpair these. So this is the ground state. So it was proposed that maybe it just goes to an excited state.
I don't think that makes sense.
Well, there's not much difference in energy here, so maybe the extra stability by bonding in with the hydrogens, okay, to where then we could have the carbon with its s orbital and its, well, I need to make it bigger. With its s orbital and then its p orbitals, we could have now a hydrogen come in here, a hydrogen sigma bond here, a hydrogen sigma bond here, but then we'd have to have another hydrogen sigma bond with the S, and just from a logistics point of view, it's pretty hard for that hydrogen to come in. You put a hydrogen here, 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 and here. But that would make 3 bonds identical, and they would be at 90-degree angles. And then you have 1 bond that would just kind of be cramming in there that would be different because overlap of s orbital is going to be different than s and p, slightly different energies. You'd have 3 bonds that are identical, one's a little different. Well, all 4 bonds of CH4 are exactly the same. So this is what we call the excited state. But what happens is the electrons hybridize. The core electron doesn't do anything, but then we end up getting 1, 2, 3, 4 sp3 hybrid orbitals with 1 electron into each. This is the hybrid state. We get 4 equal degenerate orbitals that are all pushing apart. So the 4 orbitals, the hybrid orbitals, are going to be your sp3 hybrid orbitals. And they're going to orient themselves. Oops. Losing atoms. Okay. They're going to orient themselves just like this at the corners of a tetrahedron. 109.5 degrees. 4 things that hate each other. The 4 orbitals, that electron pair repulsion theory, the 4 that can get the maximum distance apart is going to be in this tetrahedral arrangement. So here's your hybrid, sp3 hybrid orbital. Now why is it sp3? Because the s and all 3 of the p's merge together to get 4 equivalent. They're going to be slightly more energetic than an S, slightly less energetic than a P. They're right in between. They're hybrid orbitals. You've combined the S and all 3 of the P's, and we've gotten 4 equivalent hybrid orbitals now. So we end up then getting a carbon with a hybrid, sp3, 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 hybrid orbital with a hydrogen, sigma bond, sigma bond, sigma bond, sigma bond. So you get 4 equivalents. So the valence shell electron pair repulsion theory is going to cause the 4 pair of electrons to all shift. Now we can apply this principle to many different atoms. Okay? So I kind of go through here. This is 2, 3, and 4. I just kind of explain everything about the ground state, excited state, hybrid state, right there. Okay? Now, what if, instead of being CH4, it's ammonia, NH3? Well, nitrogen is going to look like this. Okay? So if I did its Lewis dot structure, I'd have here here, here, and here. Now it seems easy for NH3 to come and bond like this. So if the 3 hydrogens came in here and bonded and made NH3, what would my bond angle be in NH3? If it bonded with the 3 electrons in the p sublevel. How are p orbitals oriented? Px, py, pz. So the bond angle would be 90 degrees. But the bond angle in ammonia is not 90 degrees, it's 107.3 degrees. How can that be? Hybridization. So we do the exact same thing. Okay? We do the exact same thing. Promote an electron up, but this time it's going to end up being paired. Okay? Well, we promote an electron, yeah, it pairs up here. Okay? But now when they go to hybridize, now we get 4 equivalent orbitals. It's just still hybrid, 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 hybrid. It's just one's a lone pair. Hydrogen, hydrogen, hydrogen. Sigma, sigma, sigma bonds. Okay? You guys got to get used to it. I'm going to say it 1,000 times. Okay? And so as a result, now remember the bond angle starts at 109.5. But this lone pair is going to swell and push these a little bit closer. About 2 to 3 degrees, the bond angle is going to decrease. So 107.3. Now you don't need to know exact bond angles. You just need to know it's slightly less than 109.5. Okay? It's going to be different for every molecule. You don't just, lone pair occupy a greater space than bonding pair, so the bond angle is going to be slightly decreased. We look at water. Water, oxygen, has 8 electrons, 6 valence electrons. Okay? Looks like this. Again, if we made water bond here with this 2 unpaired electrons in the P, hydrogen came in here and hydrogen came in here, both bonding on a P sublevel, what would the bond angle be in water? 90 degrees. But it's not, it's 104.5. So what happens?
There's 2 lone pairs, so it's 2.
Okay, here, so we have hybridization. So we have the oxygen, hybrid, 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 2 lone pair, 2 sigma bonds. Ha 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 ha. 2 sigma bonds, okay? And so now the bond angle, 2 lone pair pushing.
So it's 2 degrees.
So 2 to 3 degrees per lone pair, it's 4 to 6 degrees. So we go from 109.5 down to 104.5. Okay? What if we have a double or triple bond? Turn the page in your notes. I'm not going to turn the page. Okay? Okay, so let's just say that, okay, I want to make C2H4. When I do the Lewis dot structure, it looks like this. So it's sigma, 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 pi, sigma, sigma. Okay? A pi bond, what's the only type of orbital that can form a pi bond?
P.
P. Hybridized orbitals do not form pi bonds. So somehow, some way, when the carbon goes to the ground state to the excited state, now one of the p orbitals has to remain unchanged. So instead of having all 3, only the s and 2 of the p's, so we end up getting 1, 2, 3 hybrid orbitals, but 1 unchanged 2p. 1 electron into each here. So now when you look at the carbon, it's got 3 hybrid. Well, 3 things that hate each other are going to get in a trigonal planar. They're going to get at 120 degrees. So this carbon's going to do the same thing. Sigma bond, hydrogen out here, sigma bond. So the sigma, The hybrid orbitals determine the shape. But each carbon now has a p orbital. Let me do it in red. Time just goes too fast. So now, so we have a flat molecule, but we have a p orbital that's perpendicular, unchanged. They can overlap side to side, and that's going to form your pi bond. This is sigma, 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 haha, pi. This is one pi bond. Okay? So when you look at that, it's going to look like this. To where here's your carbon and carbon, here's your sigma bond between the two carbons, sigma, 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 ha ha ha, and your pi bond. The overlap of the p orbitals side to side. Okay? So we're only going to play dot to dot with the nuclei, so we say it's going to be a flat, a planar molecule, where we're going to have a cloud of electrons above and a cloud of pi electrons below. They're delocalized, they can go anywhere above and anywhere below in that. But that's the weak bond, that's the one that's going to break. If you break up one of the two bonds between the double bond, it's the pi bond that's going to break, not the sigma bond. Sigma bond is the much stronger bond. Okay? Now when we have a triple bond, in C2H2, you got to have two pi bonds. So in C2H2, instead of this, that's sp2 hybridization because the s and only two of the p orbitals hybridize. Here we have to have two p orbitals unchanged, so we only have sp hybridization. And so here's your sigma and sigma bonds going, so it's going to be AX2 linear, and then you're going to have a p orbital on Y and p orbital on Z. Overlap, so this, like pigs in a blanket, it's going to be surrounded by pi electrons. Only p orbitals, non-hybridized p orbitals, can form pi bonds. So we have sp hybridization. Now, anytime you have AX2, it's always going to be sp. Anything that's AX3, it's going to be sp2. Anything that's AX4, AX3E, AX2E2. Anything with 4 pair of electrons around it is going to be sp3. So the application of it is very simple. The explanation of it is not. The good news is you only have to do the application. Y'all have a great weekend and go Jags.